So partially, some of the results in our today's presentation will be part of one of the project called MPP Lab, Mathematical Programming in Parallel Laboratory. It's a part of the NSM project, National Supercomputing Mission Project. The aim is that the project title in detail, high impact applications of optimization and statistics on multi-petaflop systems, and then applied to teletraffic network application. This project is part of CDOT, IIC, and CDAC Pune. So I'll give you some overview about this real-time project for 5G teletraffic network application. And I also discuss various issues from the data processing, data extraction, high-performance computing, and control the network. The project is designed by Dr. Narendra Karmarkar, a legendary scientist and distinguished scientist, and then software persons from CDOT are involved. So what is important is 5G and beyond wireless communication challenges, where we talk about the routers, switches, and cost, capacity, bandwidth, and communication algorithms. And every 5 minutes, if you take the snapshot, the data explodes in the GBs and terabytes, then how high-performance computing can be really used. So that is what one of the focus in the today's my lecture. So if you really see 2G, 3G, 4G, now if you see 5G and beyond, you have the more wireless mobile networks and different kind of messaging, different kind of chatting. All this data we need to integrate with the high-performance computing systems. And this data is changing for every 5 minutes, 10 minutes. The question comes, how do you model this entire data? And how do we process the data? And how do we control the telecom networks? And then how do we take a decision to change the complete network traffic? These issues. When you say integration with high-performance computing, these all come under the large-scale mathematical models, graph theory approaches, and multi-commodity flows. These are the things which we have to use it. So now question comes, do you need high-performance computers? Because in 5G and beyond 6G, if you see, we need supercomputers where they can handle real-time 24/7 data processing. So 5G and beyond, we have communication challenges. Similarly, we also have data processing challenges. All the data is 24/7 only. So how we put all things together and we discuss actually what are the issues we need to understand. So almost all the traffic engineering application, you can model as a multi-commodity flow. Multi-commodity flow, which is extensively used in the transportation. And today, multi-commodity flow is used in the many areas, finance departments, banking sectors, and then power generation. Everywhere we use the linear programming and optimization, where we solve few million variables. And to solve the few million variables optimization problem, you require powerful supercomputers. So we need to understand all these things actually. So as I explained in the beginning, this is the part of the some NSM project. Let's see how this look like is how this 5G, 6G data can be really handled. If you see, you have the two high-speed links coming from the telecom servers. That's what called the telecom network data extraction server. And these telecom networks, they directly connect to the data extraction server, where the data extraction server gets the data, and data extraction server also can send back the information to control the switches and routers, everything. This data extraction server data is pushed to the supercomputer. That's what the highly specialized supercomputing system, which is based on the unified architecture. Now, when the data goes to the supercomputer, it has very powerful optimization algorithms. These algorithms will be run on the powerful supercomputing system. Then, when they run this optimization algorithm, first they construct the traffic matrix. Through traffic matrix, they run the algorithm on the supercomputer system. The algorithm output gives the how the traffic patterns, how the routing can be optimized, the routing from source to destination can be changed. And this is a continuous process. That means here you control the network, you get the network traffic data, extract the telecom data from the, and then move to the, push to the supercomputing system. Supercomputing system run the linear programming algorithm, mixed integer linear programming algorithms. That's where multi-community flows. And it comes out with the optimal routing path from source to destination. This entire process runs with the 24/7. And then every 5 minutes, we can take the snapshot of the data, or every 10 minutes, we can take the snapshot of the data. That is how at the conceptually higher level understanding of the data processing challenges in 5G and beyond, actually. Now, if you really closely see, the supercomputing system should have a most powerful compute nodes. These compute nodes may be multi-core processor servers, each having many kind of accelerators, CPUs, GPUs, and then signal processing processors, FPGAs, all these things. So now the supercomputing system is directly connected to the data extraction server. Through data extraction server, you can control the entire network. So this is what happens at the high level of understanding the how the high-performance computing system is really tied up with the 5G telecom network traffic, actually. If you really see the kind of applications you have, internet applications, video conferencing applications, and you have the messaging, and you have mission-to-mission applications, you have security, many are there, actually. If you really see one level below, then you have the different kind of networks, and all these networks will be available, actually. So now, one question is, how do you integrate all these networks, and how do you do the math model? Second one is, how do you estimate the overheads? Third one is, how the message goes from source to destination. That is called minimize the cost moving packet from source to destination and maximize the flow. How do you really model this thing? That is also equally important. Now, if you see much higher level, you can really see that you have the one side, one application is there, and you have the data extraction servers, which are geographically scattered. All the data extraction servers, they are connected to the one way to the telecom network, other way to the supercomputing system. And you have the edge routers, you have the core routers, you have the access switch, you have the network load. That's how the actual network. We can model all these things as the graph theory models. So now here, the data which we gather every 5 minutes, every 10 minutes, we can get the telecom traffic data. In this project, we develop a math model. We develop a math model. The math model, we fine-tune the math model so that if you really get the traffic metadata at various points of time through the routers and switches, how close it is actually. So that is also we need to do actually. Okay. So let us see more details actually. Now, if you look into the much higher level in the telecom domain, you have the data packets, you have the router control sector, you have the voice processing, and you have industrial IoT processing. And all these things are connected to the through data extraction server supercomputing system. The supercomputing system will have the many libraries, scientific computing libraries, which we'll discuss. And we have the GPU sector processing, we have the FPGA sector processing, we have the CPU sector processing, all are available actually. So that means what? The supercomputing system which we design is a unified architecture supercomputer where you can process the finance application, banking application, power generation application, but we are now focusing on telecom traffic application. So now let us see the vast amounts of data generated by these are wireless communications. 5G wireless communication combined with the increasing supercomputing power generated by the high-performance supercomputer. What does it mean? Every 5 minutes, every 10 minutes, if you take this snapshot of the data is exploding. That means early morning, 12 o'clock to morning 6 o'clock, you may find the less amount of data. Maybe morning 6 o'clock to 8 o'clock increases, morning 8 o'clock to evening 5 o'clock, it increases completely. Then how do you process this data? That means what? To process such a huge data, human being knowledge is required, artificial intelligence knowledge is required, both come together, then only we can solve real-time traffic application in the telecom actually. So now, the other side is that most critical to the telecom network infrastructure is security. Second one is control of entire telecom network. Then what are the other issues we need to understand from the security point of view in the nation is digital economies, social networks, national infrastructure, financial systems, cyber system. So that means all these things, they use 5G, 6G telecom network. And then if there is any, many remote attacks may happen, and these systems will be vulnerable to the many other unknown resources. So national security is very, very important. So all these things is nothing but real-time data processing is one, network control is one. These things we need to understand and do it actually. So to do both the things here, you need human knowledge, artificial intelligence knowledge, as well as you need a supercomputer. The supercomputer should monitor the traffic, control the systems, and then some of them may be available on the cloud. All these things can be required actually. Now, what we plan to do in this MPP lab project is we would like to analyze real-time petabytes of simulation, and it has a lot of good mathematical libraries we use it, and then it provides a chain of innovation where the algorithms, libraries, parallelization, telecom traffic, everything is integrated together in this process actually. So presently I am discussing at a higher level. When we go details, then we get idea. So now this is how at the second level is that you have the telecom network probes, and you have the compute cloud is there, and you have telecom middleware with HPC libraries integration, compute cloud with HPC integrated. Then you have the application programming APIs are there. Then your telecom traffic analysis is there. And first and foremost is data extraction server. Data extraction server is directly connected to the supercomputing system. Then you have the telecom middleware and you have the telecom hardware part, that is NICs part, modified router switches, network flows, everything coexists actually. When everything coexists, then how we can really solve the actual application, that is very, very important actually. So now you see, for example, here, as we discussed earlier slide, you have the telecom networks are there. They are connected to the data extraction server. Then you have the optimization algorithm running. The optimization algorithm also uses many libraries on statistics, linear algebra, graph theory, and network flow library. Then, after running everything on the supercomputing system, then you get optimal routing path. Then you run the extract information. That means how the optimal routing path will tell you to change some configuration of the entire telecom network. That's what smart algorithms. After that, you have the network control parameters. Then again processes. So this is a continuous process actually. Because of this continuous process, you will be in a position to understand how the traffic is moving and everything. So now if you see much more details, what you really see on the extreme left is the physical topology of the telecom network, which I have synthetically created from the BSNL data or some data available as open source. What is required here is that this model has a graph. Graph consists of set of OD pairs, and they have the cost and capacity, and they have demand also actually. That means from source to destination, we need to, we know the cost capacity, we also know the demand. Demand means in a high level understanding how many number of phone calls are going from source to destination. In other words, how many bytes of data is moving from source to destination. In other words, how many packets of data is moving actually. Now, if you have 20 cities and if you all are involved, 20 into 19, 380 OD pairs are involved in communication. Now we model this one as a telecom network graph. That is called there's a graph is there actually. The graph. We consider undirect graph, cost capacity, we have vertices and edges. Then we build the traffic matrix. That's what the typical traffic matrix look like actually. Once you build the traffic matrix, then you process the traffic matrix on supercomputer with the linear programming algorithm. That is what mixed integer linear programming algorithm. Then it gives the optimal path. That's what the optimal paths are there. With this optimal path, now the supercomputer will design intelligent algorithm, tell the data extraction server that you have to change the configuration separate in a different way so that network traffic is very smooth. Once you complete this one, again you start. See, that means every 5 minutes or 10 minutes or 15 minutes, you take a snapshot of the traffic and you go to your mathematical model, and mathematical model validate with the actual data. Once it is validated, then use the mathematical model and know the number of OD pairs who are involved in communication. OD pairs means, good example is you take 5 metro cities in the country, India, Mumbai, New Delhi, Calcutta, Chennai, Bangalore, Hyderabad. If you take 5 cities and you have the 5 into 4, 20 is there, then we construct the traffic matrix. And demand means you give the traffic. How you give the traffic, that we'll discuss maybe in subsequent slides. That means how many phone calls are going from one city to all the 5 cities, all the 4 cities, at what time, and how do you convert the number of telephone calls to the packets and MB and transfer the data. All these things are nothing but pre-processing of the entire application. That's what telecom math model we develop. and we get the real-time data from the real-time data or the historic data which we get from many of the telecom vendors. Then our math model is validated with the data and process it. So various stages. One is representation of graph with the entire data. That means the graph data will have the number of OD pairs and cost capacity and demand. After that, it has to go through the construction of traffic matrix. The traffic matrix, basically you will see how the vertex and edges, the interaction, everything. After constructing the traffic matrix, then you run the linear programming algorithm. When we do all the things, data extraction server is directly linked with the telecom network, as well as the data extraction server is directly linked with the supercomputing system. The supercomputing system will have the powerful head node of maybe 512 cores or 1000 cores. And they will do some pre-processing. Then they give the entire application to be run on the distributed computing system that is having more than 160 nodes. Once you compute everything, then you get an optimal solution. Here we indicated in the red color, source to destination. Now this optimal solution, and again you interact with the data extraction server to control the complete network. So these are the various stages which happens in the entire software actually. To do all these things, we need many libraries. That is called statistics library, graph theory library, linear algebra library, machine learning library. And these libraries are designed such a way that whether you have finance application, whether you have the telecom application, whether you have power generation application, whether you have manufacturing application, libraries will be used extensively in the middleware stack actually. Sometimes we may use system-dependent libraries. Sometimes we use the your own libraries actually. So it is all very much essential when we really do the actual job actually. So now let us see from the other side, telecom network infrastructure. What are the issues we need to understand, we need to do. So what we have seen at a higher level, how the telecom networks, how the supercomputers, how the data extraction, how the telecom traffic represented as a traffic matrix, how do you solve using linear programming, and how do you control the network. Now we go more details about each and everything carefully. So that means what? How to control the entire infrastructure in the telecom is a great challenge. More heterogeneity and different kind of communication patterns, and then different kind of data integration, everything. So now in that case, when the data is fully open, we need to worry about the security aspect of the data, privacy aspect of the data. This is also very, very important. Then question is, when you use supercomputers connect to these telecom networks, how do you really monitor the communication traffic? How metadata can be obtained? And how do you collect the data? And how do you analyze the data? How the traffic flows? All these things we need to understand. Most importantly, here in the entire telecom network, under the round the clock it operates. That means 24/7 operations keep on going, and we need to have a lot of programming aspects to make sure that this overall data analysis is done correctly. Now question is, why do we need HPC system? The HPC system, which is integrated with the data extraction server is integrated with the telecom network. HPC system is having large, powerful head node with shared memory. HPC system is having a large distributed cluster. And this entire thing will see safety, security, privacy, and data processing. All things are really important when we do this kind of supercomputing integrate with the telecom networks actually. Now let us see how the data processing is done. Most of the many basic fundamental problems on communication networks require optimization techniques. Only do optimization techniques, what we call mixed integer linear programming. That means what? Use traffic analysis and develop algorithmic automatic techniques to dynamically reconfirm the virtual network topologies. If you're able to do, then you can control the hardware and software of the complete telecom networks. That means what? Basically, we need to find out optimal virtual networks topologies. How do you really determine the optimal virtual network topologies? How the traffic monitoring is done at regular intervals, how the traffic monitoring is data is collected, and how the telecom switches, routers, telecom network flows are built and inserted in this entire network. So all things happen from the telecom side is a lot of integration of heterogeneous devices, and gathering data and modeling as a mathematical model is another part. Solving these models of graph with use million vertices and edges on supercomputing system is another part. And control the network with the optimized routing algorithm is another part. All things should go parallelly actually. Now let us see, when we have the data means what? Every 5 minutes you get the data from the data extraction server to the head node. The head node is having a huge amount of memory, more number of cores. Then how hardware part and software part can handle the cache coordinates, everything is important. How the hardware, how the system will help to check how the routers need hardware or not. How the extraction of data, that is data extraction server, is going input to the optimization algorithm. And then once the output comes out of the optimization algorithm, how do you control the network? So these are all partially with the telecom side, partially with the HPC side, everything is integrated now. That means we need a most powerful high-performance computing system to handle the large amount of heterogeneous data and then run the optimization algorithms and control the network. All things are tightly coupled actually. So now, how the supercomputers are built? Now, if you really see, we have the application side, voice processing, data processing, IoT processing, router control. All these applications require different kind of memory requirement, different kind of data challenges. How do you accommodate all these things? Also very, very important. Now, I'll skip a couple of slides. These are the large kind of systems which are available maybe around 15 years ago. What we call C-rack Paramviva. They have the many racks. Every rack is having 8 nodes, and every node today we have many GPUs. So these are the systems to monitor the real-time traffic data where they run the optimization algorithms and everything that we'll discuss more. Now, if you do not have this kind of data systems, then we can hire the systems in the cloud. The cloud also provide different kind of hardware, software, network, and different kind of services also. And then how to build these supercomputers? These supercomputers build, there are two approaches. One is bottom-up approach. That means you purchase the hardware, software, integrate all the systems, then you run your applications. But your application really fit into all the requirements or not, which we are not checking. So that's a bottom-up. Top-down means what? I have this special kind of telecom traffic application where every 5 minutes I get the large amount of data and I need to process, model the data as a telecom graph. And then from graph, I construct the traffic matrix. Then I run a linear programming algorithm. All the things, nothing but you build a system based on the algorithm, based on the application requirements. So that's where the top-down approach. We use a top-down approach for implementation of such kind of 5G beyond teletraffic engineering applications actually. Now, from the telecom side, what we really see, what is required when we process large amount of telecom data? One is traffic engineering is one. Network behavior, understand the congestion, bottlenecks, reliability, which we'll discuss. And optimal design, what is the capital investment? what is the maximum robustness? Optimal operation, optimal routing of telephone calls, data packets, minimizing operating costs, all the things are required. These also calls multi-community flow. Minimize the cost, maximize the flow actually. So that's what very, very important. And this is very, very useful in the designing complete system for 5G and beyond. So system means here high performance computing system is required to process the large amount of data which comes out of the telecom traffic actually. So now I will give you other slide. Second portion I'll talk about the second one. Am I audible now? So let me continue. So here there are four independent blocks are there when we process this application. One sec. One is how do you really extract telecom data as input to optimization algorithm running on a powerful head node. That head node will have the 32 sockets, will have the 32 cores, and we have the more than 1,000 cores. And then we develop the math model. The math model is represented as a graph. Graph consists of set of OD pairs, cost, capacity, and demand actually. So the first block is basically about the input, data preparation, everything. Now, this data is changes every 5 minutes and minutes. We need to store the data also. The data also we use the database storage we use actually. So you can extract the data at what time, what is the traffic, everything. The second part is how do you build a traffic matrix? How the traffic matrix is there, how the network topology. That means you have the data and network topology, both you pass it on to the optimization algorithm. That's what the network flow solver. When it runs, it gives an optimal routing path actually. Once you get optimal routing paths, that's what in the stage number 3, you get the optimal routing paths which have been indicated with the red color actually. How do you get this optimal routing path means? Here if you take 10 OD pairs, 10 in 10 OD pairs means 10 into 9, 90. So 90 you have the 10 OD pairs means source to destination you have 10. Then how the message travels from source to destination, what are the various paths, everything, there's all things also stored. So that means in these 3 blocks, if you see data gathering, data processing and data extraction server, data gathering, modeling the data on the head node, processing on the cluster node, and before processing, we need to understand the telecom traffic matrix, and we need to understand how to store this data in every stage. These are the things. Last block is you are running the optimization algorithm, which may have the few hundred million variables on a large cluster. The data will again go to the output of the running optimization algorithm gives the optimal routing path. That means what? What are the current set of demands in the traffic? And when we process these algorithm on these systems, it comes out with the what are the best alternative paths. All these things will go to the data extraction server. There we run again intelligent server. Again, we run a very intelligent network algorithm that to control the entire network. That is run on the head node. After that, data extraction server picks up the data and now change the hardware, routers, everything. That's how it happens actually. But in all these things, presently, because of security and privacy reasons, you get the BSNL data or the Airtel data, metadata you get at the routers and switches. Since we develop the mathematical model will validate and mathematical model will fine tune so that it is very close to the real time data historically happened 1 hour or 1 day actually. So 1, 2, 3, 4, these blocks gives the overall process which we do the 5G real time data. Okay. So now one approach is either you synthetically generate the data using graph theory, statistics, and other graph statistics algorithms, Second one is that you can collaboratively work with BSNL, Airtel, and other telecom vendors, and try to see how metadata at the routers and switches can be processed. So both can coexist actually. So that means what, if you really see, getting the telecom data, modeling as a graph, then define the cost capacity, and understand the every OD pair, what is the demand, and then how to get the traffic matrix. The traffic matrix, every vertex, you take care of the adjacencies, then you can able to get the traffic matrix. Once you construct the traffic matrix, then how do you solve this entire thing? That means you are solving, to solve the entire problem, you require two things. One is the data, that is what the traffic matrix. Second one is network topology. By both the things as input to the linear programming, that is called mixed digital linear programming solver, you can find optimal routing paths from source to destination. Then you come to the 24/7 network control also. So there are 4 blocks that gives the overall idea. In all these things, the most powerful system is head node. We have 1000 cores where it does a lot of pre-processing. Head node data moves to the cluster having 160 nodes. That is also there actually. Now, if you really see, if you take the 5 or 6 metro cities and try to find out the traffic, everything. So what I'm talking is high level issue, high level. The high level is data extraction server. And then you have the Mumbai, you have the Calcutta, you have the Delhi, you have Hyderabad, Bangalore, Chennai. So all these things, you see, there are 6 cities are there, 6 OD pairs, that is 6 into 5, 30. Everybody is communicating to everybody. Then how the data access server connected. From data access server, how the network is connected. All these things are basically at the next layer actually. Okay. So this is how the program look like actually. Now here, how to get the data from the telecom networks to data access server? How the data access server control the network? These things are very, very important. So that way you see each data access server have multiple cores. Because of having multiple cores, you can able to write multi-threaded socket programming and get the data also. So what you really see is that the data which you get it from the data, once you get from the data access server, you can run the supercomputing application optimization algorithm by constructing the traffic matrix. Then you get the optimal routing paths from source to destination. So what you see left side is basically, these are the pool of resources, and you have the different kind of data action servers available at many cities, many metro cities. They process the data. So now we already expressed about this one. Let us get more details also in this actually. So what is the major important thing in this is, how do you define your mathematical model, which is very close to the actual telecom data what we get. That is called telecom math model validation. Second one is how accurately build the traffic matrix. The traffic matrix, then we process on the powerful system. One is that data type. Second is that topology of the data available. Both the things which is input and process it actually. So when we do all these things from the programming point of view, what is important is, if you really see 25, 30 years ago, people use statistical methods and like Gaussian Poisson methods. Now, if you really see the live telecom network data, you have to model as a graph, is that data streaming happens, and how do you do it? Or if you develop your own synthetic data, generate a large graphs of 1 million, 2 million, 10 million graphs, undirect graph, and measure the cost capacity as well as the overall demand, how much data I move from source to destination, all things we need to bring it. That's what Synthetic data you can do. Once you do synthetic data, your telecom math model with the synthetic data has to be validated with the real-time data. Since getting real-time data is very difficult because of the security and privacy, maybe one day back or 2 days back data, you correlate it actually. Other one is live telecom network. Live telecom network data, you get it, then you process it, and once the data action server process it, it goes to the telecom traffic matrix, then it executes that telecom traffic matrix with the network topology, then it gives optimal routing path, then again control the network. So this is how it happens actually. Large amount of data is there in our Indian context. We have the BSNL data, RailTel data is there. You can use these things also. Many other open source software also available, Abelian network, European network, and then many of the BSNL topologies also available. And how do you process all the things? So validation of math model, graph-based telecom networks, build traffic matrix, and understand the network topology. Then when you do all the things, the data is very used. You do the data for every time interval every day. That is number of hours, number of days, number of weeks, number of months. And you have the libraries of linear algebra, graph theory libraries. Then once you have the complete telecom data, then you integrate with network topology, then solve for the optimal routing path. So this is how it goes actually. Same thing I'm giving. Now what we do, we also cover something on the more details about the what happens when we really implement this software. Let us see. The network control is the most important thing. That means you have the data describing the complete traffic, and you have the topology. And then when you represent the data of the entire traffic as a graph, then you also have the cost. You also have the capacity to move packet from source to destination. Cost means time taken to send a message from source to destination. Cost capacity, and what is the demand, how much is the traffic is going in this route. These all things are very, very important actually. This is called network flow module. The network flow module, they call network flow algorithm. That is also called as the multi-commodity flow, how we can solve actually. So what you see is the traffic model interface, network flow, and you have the linear programming AMPL. We used it for in this as a simple AMPL program. We used it. AMPL is a linear programming and optimization. It's a language based, and it does all the optimization algorithms implementation. Now what you really see is little bit advanced one, which I am telling. Left side you see the Indian map very close to India, and you have cities, and you have some communication goes from every city to other city actually. Now the question is, how do you measure that? How do you calculate the traffic matrix? Synthetically generate the graph. Synthetically we measure the assign the cost capacities, and then come out with the final thing. So what we do, we define a mathematical model for all the things. The mathematical model which I'll explain. In this one, city 1 is population is I have given some data, longitude, latitude, and city 2, Bangalore also given. Now what are the distance between two cities, and what is city activity, and what about the population product of both the cities, and what about the product of population and activity. All these things are very, very important to do the telecom math model actually. What is telecom math model, which we discuss also. Below you see the traffic matrix. Right side you can see how many bytes of data is going from one node to many nodes actually. So all things shows that there is a huge amount of terabytes of data is moving out of the network every 5 minutes or 10 minutes. I will just quickly cover something else, then I'll come back to these presentations. First we talk about the telecom math model. What is the telecom math model? Then you get idea. From that we can see actually. So what telecom math model? How to emulate the traffic of density between a pair of cities? How do we do? Given a graph here on right side, on the right hand side, you have 20 cities have taken. The curly bracket indicates the degree of the each vertex or some other parameters. Now you have the graph set of vertices and edges, and we talk about the cost capacity of each edge, uh, and also we talk about the what is the demand traffic demands are there, all the things we need actually. Okay, here you can able to see the complete graphs. The graph modeling is very important. That means you construct a graph, you construct the edges and edge weight, vertex weight, cost capacity, all things we need to set up carefully actually. Huge amount of time is spent on pre-processing actually. Now question is, how do you measure the traffic? In this example, we have taken only one day, that is 24 hours. We take 20 cities, what we shown in the picture, and we have constructed time intervals 48. 48 means basically 24 hours are divided into the 48 intervals. Every 30 minutes, I take a snapshot of the network. And first network data, I gather it directly from the site and process it on the NSM, our HSM systems. When you process it, then some data will be running on the cluster. That's all. Now here what you see is that how the data has been gathered, how the data is represented as a graph. These are very important in telecom actually. So now let us see more details. What are the four activities? That means what we are saying from the beginning, for 5G and 6G, if we able to capture the data, and if the data comes to the one of the powerful ad node through data extraction server, then we can see the traffic and we can optimize the routers and everything. But when you have a large cluster, more than 100, 200 nodes, and if your message goes from here to many places, for example, Mumbai to Guwahati, there's a time zone will be there. And activity means Jaipur to Delhi, every Diwali, there is a lot of activity, traffic is more. And affinity is also very important. That particular place, how you are trained to do certain activities actually. Time zone, what is the time here, what is the time in Guwahati, and how do you map? All these things are input required to define the mathematical model. Then you validate the mathematical model. Then you copy onto the other system and run on the actual server. Now, if you really do all the things, what kind of modeling it is done? How do you validate this model? Whatever traffic data we get at morning 10 o'clock or 12 o'clock or 9 o'clock from the telecom data, is our data is very close or not? How tensor matrix is highly optimized? All things are very important. So that means my aim is to emulate traffic between the two pair of cities. So what we required, population of the city 1, city 2, and product of the population, and activity between these two cities. Any activities are there, for example, Diwali or the Ganesh festival or some other Dasara vacation, the traffic is more from one place to other place. How do I identify it actually? Activity levels also very important. Now, when we calculate the product of population, product of activity, product of density, product of the all these things, we finally get the model up. So this is how the model actually. So that means you have New Delhi population is this much. They have longitude, latitude, and language time zone also varies. And then Bangalore, this much is a population. What is the distance between the cities? What is the population product? What is the activity? What is the traffic density? Number of class? All things we can analyze on the graph, which is synthetic, undirect graph, represent only 20 vertices here actually. Okay. So same logic we apply for the another real-time data to get the good results also. Now you see, you run telecom math model. The telecom math model is there. Root telecom math model is one. There we talk about the two cities, OD pairs. Here in this example, New Delhi and Bangalore, longitude, latitude, as well as the language, distance between two cities, and city activity, and all these things we get it. And ultimately, we say this is what the uh, traffic representation actually. Okay. We also discuss about the traffic density, that is product of the population and activity, product of the various products which we defined earlier in this slide, product of the population, product of activity level, product of population activity level between the. Now we'll go a little bit. So now that means what is entire graph in Indian thing, if I fill with the if, some points, each point represent number of phone calls going from origin to destination. Then main aim is that how to find the shortest path from origin to destination to minimize the cost, maximize the flow. That's how we define as the graph for this actually. So now we will we'll take some 3 minutes break, then we'll get back actually. 3 minutes break we take, then we talk about the how the mathematical model is really built actually. Two minutes break.
We'll just.
Hmm? Share.
Cheers. Screen.
Whatever.
Full screen.
Okay, no? Why you're checking there?
Okay, what's it?
So now, how do we get this telecom traffic data? If you take complete 10,000 cities, if you take 10,000 cities, then you have many OD pairs, that is 10,000 into 9,999, that many OD pairs, and then we need to find out the cost capacity of every edge of the network. Then we should also know the demand. How we get the demand, that also will show you in the next part actually. Then in real time, we take every 5 minutes, 10 minutes about the traffic, but now in this we take only 30 minutes. But in real time, minute by minute activity levels, we need to be considered. So that's very, very important. So what we really do in this, in our mathematics, that means the mathematical model of the telecom traffic is one of the novel method. And actually, how do we get the traffic? The traffic, even though we get metadata, but the complete traffic data, because of privacy and security reasons, call records may not available. But if we get the data previous day, then we can fine tune our model, validate our model, then the model becomes more robust and model will be directly used also. Now we should know about the population, how the traffic means based on the population, latitude, longitude, language, distance, population product. Many factors will be considered to represent the traffic. That's what we do here is that population of one city, one and city two, that's a OD pair, activity level between the city one, city two, population of product of population of activity and product of activity and affinity. All these things build the total traffic between the OD pair, between the city 1 to city 2 in OD pair actually. That means what we need to consider is activity level, affinity level, time zone, coordinates, language, index, activity level. All these things we consider and come out with the traffic representation. Then we also see the population of the every city, and then we can measure the traffic. Now, the next I will give you a little bit worry about the other side of the traffic. That's what called the, how do you really convert the number of phone calls and how do you get the actual traffic? That also we'll discuss actually. So come back to the first one. So how do you convert the traffic means measured in the packets or the bytes. So how do you convert the number of phone calls into the respective bytes and how do you do it? So what we really observe in this, if we see the earlier presentation, how to get the represent the traffic, where the traffic is represented as a graph. Graph consists of set of OD pairs, cost and capacity, and demand, and then we represent as a graph. Then we construct the traffic matrix where the demand is also included. The traffic matrix is solved on the supercomputing system where we use the linear programming, mixed integer linear programming algorithm. That's what we call as multi-community flow. It generates the optimal routing path. Then optimal routing path, again move to the, you do some intelligent algorithm, smart algorithm you design. That algorithm will automatically reconfigure the network control, physical topology to make the total traffic very smooth. That's where the data extraction server is used actually. And these are the things which we represent the model. We need the affinity, the activity, and time zone and mapping actually. Now let us see, we also walk through one slide about synthetic graph with 20 cities and synthetic graph with 20 cities, and we would like to see the traffic actually and how do you convert actually. So let us see. What really shows is that from midnight 12 o'clock to next day night 12 o'clock, various time intervals are there. In some time interval, 10% of the population is involved in the telecom traffic. Morning 4 to 8 o'clock, maybe it is very high. Morning 8 to 10, it's very high. Morning 12 to 14, afternoon 12 to 2 o'clock, it's very high. That's how the traffic goes from every city to every other city. And then we store this entire traffic using Berkeley databases. Now let us see. Now that is what, if you really see time interval 20, time interval 20 falls between morning 4 a.m. to 8 a.m. Morning 4 a.m. to 8 a.m. Then you say total 20% of the city population is in the telephone conversation. That means they keep talking to many citizens in the many places. Then you have the city 1, city 2, number of phone calls. Then you convert into packets, packet into the bytes, and that's how the bandwidth also you require actually. Okay, this is how the traffic now. Now let us see. Now that means what? Every phone call you can convert into the bytes using different kind of methods actually. Here we are using a protocol G.711, 20 minutes, 20 milliseconds packetization interval, packet size, packets for the second level, total packets, and then you have the total packets per second and total bytes per second. Now this is how we convert. When we convert this one for 20 cities with morning 4 o'clock to 8 o'clock, this is how the GBF data. That is, you can see Mumbai, you can see Pune, you can see Coimbatore, you can see Chennai, Calcutta, Delhi. These are the traffic actually. What are the number of phone calls? And next one is what is the equivalent data in MB. So now if you really see, that means what we have done here is, in our math model, we consider the number of phone calls, convert into the MB and GB packets, and then ultimately you find out the overall graph with the set of vertices and edges, cost, capacity, as well as the demand. Demand is 143, 73, 45, 50. Now, how to construct the traffic matrix is the most important in the entire simulation actually. The traffic matrix indirectly tells about the how the traffic load and how the congestion is there on your network. That also will determine actually. Now, if you really see, now morning 4 o'clock to 8 o'clock, if you take 10% of the city population involved in the communication, morning 8 to 12, 30% may be involved. Noon 12 time to evening 4 o'clock, 60% may be involved in communication. And this is how you can have the synthetic data, synthetic graph. Here you have synthetic graph of 6 cities. Remaining cities are not really shown. Now the traffic, when you visualize the traffic, it goes like this actually. So that means what? My telecom math model, you can stress it to give the more traffic. If you have more traffic, then you can validate the model with the other networks, what we call other telecom network, abelian networks, European abelian network, then make your telecom math model very robust. What you see is visualization of Mumbai, Delhi, Calcutta, Hyderabad, Chennai, Bangalore, 6 metros actually have taken. Now we will see how we can do the next phase actually. Last we go to the linear programming a little later. or we'll go to the linear programming one sec now to get idea actually. So linear programming here, the telecom traffic data represented as a graph. Graph, a source Vs belongs to V, must be routed to a distance Vd belongs to V, and it consumes this much amount of bandwidth. That means here cost means time taken to send a message from source to destination. Capacity means what is the bandwidth. Now the path is objective is find the shortest path between source vertex and destination vertex with the capacity CUV of link with capacity of each link, and network flow constraints also there. Network flow constraints means the bandwidth and everything. Now, how do we do actually this one? This multi-community flow, it is very, very important in the telecom application. It consists of moving two or more communities between their respective source and sinks. From the beginning, we say that entire telecom traffic represented as a graph. Graph consists of set of OD pairs. Each OD pairs is then source and destination. And then each edge has got different cost and capacity. That is what the thing. And how do we really handle this telecommunication traffic? That means how do you find an optimal routing path from source to destination for every OD pair, minimizing cost, maximizing flow, and it is also called as a cost and capacity, how the bandwidth utilization is there, all these things. Okay. Now there is a traffic. Now if you see here you have the example of a typical graph is there. Cost is 4, capacity is 15, and you have the source vector, destination is there, and what is the demand and how do you move it? All these things we need to understand. So in real time, in real telecom networks, you get a cost capacity, but traffic you only get metadata. Traffic in CDR records is not possible to get because of privacy and security reasons. With this simple graph where the cost 3, 4, 6, 14, etc., and then capacity 25, 15, you can represent typical telecom network as a graph actually. Here the edge link is shared, and then after doing that, now traffic, there's a traffic flow is made up of node to, what is a node to node demand, but is one represent one city, two represent another city, or one represent one router, two represent another router, and what is the number of hops travel through 1 and 2. For example, 1 and 5 is 2 hops actually, and what is the packet to reach? Suppose if you want to send a packet from source 1 to destination 6, there may be 2, 3 paths. What is the optimal path, that is minimal path with some constraints on the network? So what we really see is that the constraint, the total flow, the constraints are that total flow along each link must be less than the link capacity. That means what? Your source vertex to destination vertex, router 1 to router 1, one city to router to another city. What is the link capacity? How much is the traffic? Is the traffic is less than the link capacity or the more than that? Then what are the alternative routing paths? Everything we need to find out actually. Okay. Always you have to keep the total flow whenever the traffic goes from one link to other link. We need to see link capacity, maximum allowed, and we need to compare also. Okay. So this is what the modeling. Now, any communication network, such as telecom networks, need to schedule message. Then what we need to address is communication network means what is it consists of broadcasting stations, receiving stations, relay stations, and then with so much amount of hardware, heterogeneous hardware and software, there is a network congestion, there is a switching off algorithms. Many are there, we need to address it in the linear programming actually. So what is our objective in the entire program is, what is the cause of delays? If there is a delay, then when you construct the traffic matrix, when you solve the optimization problem, you will see the shortest path from origin to destination. Different shortest paths are there, it will show. So all this objective is reduce the delay. Once you reduce the delay, then overall processing, packet processing will be very fast actually. Because I told you it's a complete cycle. Data pre-processing, graph representation, solving, building the traffic matrix, solving optimization problem on the cluster on head node, and then identify the optimal routing paths, then control the network. All things are 24/7 continuously goes, then we need to understand these things also. Now let us see in the traffic, number of messages of type K transmitted through the communication link, that we need to understand. That's what number of messages of type K transmitted along the communication link. And then message capacity, cost of sending a message, and net messages, all the things you put together as a commodity network commodity flow called multi-commodity flow. These are the equations we need to do maximization, minimization. So now if we really put the demand also, if we really put the, now you know the cost capacity, you have the demand 1, you have demand 2, then you need to find optimal routing paths, ensuring that each link, the total flow, each link process should be less than the link capacity actually. So these are all things we need to measure it, and we need to understand and implement it. Then only you get the optimal routing path. So that means getting the telecom data, modeling as a graph, and define the cost capacity, understand the demand, whether the phone calls are going from morning 4 to 8 or morning 8 to morning 9 or morning 9 to morning 10, and what is the overall thing we need to know, then generate the data. After doing everything, you consider the traffic matrix. Then after that, you solve this LP solver in this, where the demand is 180 and demand 180, demand 2 180 also. Then you have the complete graph with cost, capacity, edges and everything actually. So now with this thing, when you get an optimal paths, there may be several paths. 1 goes to 2, 2 goes to 3, 3 goes to 6, or 1 goes to 4, 4 goes to 6. That is, source is V, vertex is, destination is 6. How many number of paths are there? All things we need to find out actually. So this is what the multi-community flow implementation. So that now question is, do you need high-performance computing system or not? How do we really solve these problems? These are the issues. How to do it? The network represented as a graph. In the graph, each edge have capacity, cost, delay, and carry this many different commodities. That means if you have one switch here, if you have another switch here, if you have router 1 here, another router there, and the switch gathers the data, and then how it really sends the data through the router. Now our aim is to find optimal set of routes for each of the demands. But optimal set of route means min cost, max flow, that we need to see. How many number of communities? That means if you take the entire number of cities in the country, number of regions in the country, and if you really put everything together, how many number of commodities? Earlier we discussed, if there are 20 commodities, 20 into 19, 380 OD pairs actually. That means at a time, 20 cities or 20 vertices, they are started communicating to the destinations. Now, how does it go actually? How many number of commodities are there? That mathematically we can also derive number of commodities also. that is basically comes under example. If you take the typical BSNL network, which is available on the internet about the network, which has 705 nodes, edges 1583. More edges you have, then more number of paths exist from moving a packet from one vertex to other vertex actually. Now, from this, we can calculate the commodities. Commodities gives this many also there. What does it mean? As the commodities, as the number of variables increases, then you require most powerful good system to process it. Here it shows that 2,48,160 commodity flows actually. Okay. And if you really see this one, uh, how many number of vertices are there, how many number of edges are there, how they are connected, what is the cost, what is the capacity, and what is the demand. If you really measure, the number of variables are going into the billions. When the number of variables goes to 300, 400 millions, you need to solve these 400 million variables, a linear programming solver with the background of a traffic matrix, with the background of network topology. Once you solve it, you get some optimal routing paths. And when you draw it, you come to know these are the paths. So this really shows that computing size is number of variables are increasing more than 300, 400. This is all done for the one time interval. If you take a time interval, the math model which we define, it takes, you need to validate the math model. Math model takes about the language, affinity, time zone, everything. Now, once you have math model, you take the historical BSNL data or live data and compare and fine tune the model. Now, in this model, what we are talking is one time interval between morning 0 hours to 4 hours or morning 4 to 8. This is morning 4 to 8. If you really take the traffic from morning 10 to up to 2 o'clock, the traffic means 60% of the every city, they are 50, more than 50% of the every city in India, they are in communicating with the remote devices. Now 60% means based on the population, based on the conversion of phone call to the MB, we can measure how much is the data size required actually. Then how do we process it? So this is what the challenging actually. So I'll show you some other things to get the, now again, how to transfer the, suppose if there are 10% of the population is in the communication, then every phone call you convert into the packets or MB, and we have various methods are there to convert the phone calls into MB. That's what the table shows. Now you see, you can measure the, if you speak 2 minutes, if you speak 3 minutes, if you speak 10 minutes in a large telecom network, we can measure how many bytes of data you are basically processing actually. That is packet size. Earlier we have the audio separate, videos, now everything is mixed, audio, video is mixed. So there is a lot of complexity and heterogeneity to address these problems. Then total packet size we get for the particular payload actually, okay. Now you get the, that means you make a number of phone calls, you get the number of bytes to transfer everything. Then after that, you convert into the total number of packets. This is how the overall understanding of the number of phone calls and the voice or IP packets actually. After that, now we have taken example of 20 cities. In 20 cities, we have the 20 into 19, 380 commodities. Now, if you take one city, for example, New Delhi to Calcutta. Now, the traffic from New Delhi to Calcutta, are you speaking morning 0 hours to 4 hours, or morning 4 to morning 6, morning 6 to morning 9, or 9 to 12, 12 to 2? Based on that, which time interval it falls, and what is the total graph size, and 20 cities. See, number of vertices are less. Number of edges are more. Edges are means more amount of communication can be drawn from this source to vertex. Source node to the destination node. But time interval, which is on, and time, how many time on, then bandwidth. With all these things, we can able to get the overall traffic. So what you really see in this traffic matrix where network traffic matrix where the every city is communicating to every other city. What is meant by row sum? That is total number of packets incoming, outgoing, all things we measure. And what is the link capacity? What is the cost involved? What is the capacity? What is the demand? Everything we measure in this. Now, what this picture says a traffic, typical traffic matrix where you see all the 20 cities are communicating to remaining 19 cities. And all the remaining 19 cities, everybody is communicating to everybody. Because everybody is communicating to everybody, the cost of communication is very high and we need to estimate correctly. So what you really see is that column sum and other see row sum, both are there. With this, what is the total data which is moving out of the every node morning from 4 o'clock to 8 o'clock? Even though edge has got bandwidth here, vertices and edges bandwidth, the bandwidth is shared between two, vertex 1 and vertex 2. So that's what. Now this much GB is there, 1.4 GB. Now if you really put everything together, if you take only 5 metro cities means these are the 5 metro cities. Uh, 5 metro cities: Delhi, Mumbai, Hyderabad, Bangalore, Chennai, uh, and Calcutta. Maybe Bangalore must be avoided. Now what? You can take any cities after doing everything. Now this is what the overall thing. Here the affinity factor means, for example, during Diwali vacation, there is a large rush to Jaipur, Mumbai to Jaipur. During Diwali vacation, there is a lot of rush from Delhi to Kanpur, Kanpur to Delhi. During Sankranti festival time, Hyderabad to Visakhapatnam, Visakhapatnam, Hyderabad traffic. So looking into the affinity factor and time zone, that is Guwahati is running at different times compared to the Mumbai. And you also look into the various other factors, then you come to know, you can measure how much is the data is moving out. That's what very important actually. So now you summarize everything. That means what? I define a telecom math model which takes care of the population, affinity, time zone, and other factors. And between the time 8 to 4, midnight 12 to morning 4, morning 4 to 5, morning 5 to 6, I I take the traffic as a 20%, 30%, 50%. I measure the traffic, everything. Then I get the complete details, everything. Now, this is how the data. That means, if you take only 5 metro cities, and if you really put a time zone, say every half an hour, if you see more than 5 TB of data is moving. 5 TB of data is moving from every source to every other vertex actually. That means we are processing large amount of data for only 5 metro cities with having 2 GB bandwidth. But now if you take the entire country number of cities, it will be more than a few terabytes to petabytes that we need to process. We need to get a graph. We need to get the cost. We need to get the capacity. We need to get the demand. After doing all the things, then we need to get the traffic matrix. Then traffic matrix with the cost, capacity, and demand and network topology will be given as input to the linear programming and optimization algorithm. It gives the optimal routing path. Optimal routing path, beginning I said it goes to data extraction server. Data extraction server is the most important. Data extraction server, every 5 minutes it gets the data from the telecom network. It pushes data to the powerful high performance computing head node. Similarly, to control the network, the head node will run the some algorithm, highly specialized skill set algorithm that gives the data extraction server. Data extraction server internally monitors to how to change the routers, traffic, number of nodes, everything it will do. So what you really see is that particular time zone, that is morning 4 o'clock to 8 o'clock, if you take the every city population, I have only shown 20 cities. If you take every city population, your math model will tell you more than 5 to 6 terabytes of data you need to process at the time. If it goes morning 9 to noon time 12, it may go to 28 terabytes. All this data, you can get it done to the telecom math model graph theory, or you can do it using our telecom network actually. So now this is how the full data, if you really see, full data, if you see source, and if you see all the cities, then overall the data goes to TBs. Between, what does it mean? Out of 20 cities, 5 cities are having 2 Gbps connectivity, metro cities. Remaining level 2 cities, they have only 500 Mbps or 1 Gbps. So we need to understand how the network control, what is the cost all moving packet from one node to another node, everything we need to understand. What you really see is that morning 4 o'clock to 8 o'clock, if you take 10% or 20%, 10% or 8% of the population who are in communication, and this 10% phone calls are converted into the voice over IP and packets, then how do you get this? What the picture? So that means every time interval, more than TB of data goes, then we need to uh, handle the huge amount of data, and we need to store the data, and we need to process in the AMPL optimized mixed integer linear programming solver, everything we need to do actually. So this is what the true fact of the 20 cities. Now, if we involve all the cities in every state, then it will be more than 2,000 cities. In that case, the traffic must have 10 Gbps kind of traffic. Otherwise, uh, difficult. Not only that, we need to understand the link, cost and link. What is the link? Your total floor should not exceed the link. That means we need to do check and cross check at every level to process the telecom data actually. Okay. Now uh, I will also tell you about the other things. We tried with many examples. We also discussed these examples. We discussed in the beginning, there are various components. First one is how to model the traffic as a graph. The second one is how to get the OD pairs and cost capacity, and how to get the demand traffic. Then we generate the traffic matrix. That's how the traffic matrix is there with a light blue color. And then from traffic matrix, as well as the data describing the entire network traffic matrix and network topology, that is how the paths are there. We solve using the linear programming solver, that is called mixed integer linear programming solver. Then it gives the optimal routing paths. With the optimal routing paths, again you go to the powerful system. It will control the data extraction server. It will change the routers, everything. Then that's how it runs. So that means what? In all the steps, if you really see, main aim is to smoothen the network traffic. How the traffic is increasing and how do you assign the traffic is all very, very important. It's all compute from the linear programming side. Now, what you really see is we have the longitude, latitude, we have the network topology for 20. Why do we take this kind of synthetic data? Because we take synthetic data and we use a maximum memory required, maximum amount of data in MB or GB to process it. All things we can check on the synthetic data. And when you get the real data, which comes for the 1 day or 2 days before, 2 days back, that data you need to model and identify communication time, identify the bandwidth time, identify number of OD pairs, and how the all the 19 cities start communicating each other. All things we need to understand actually. So this is how the source and destination. What is the demand? What is the cost capacity? What is the demand? That also we represent here. Okay. The demand is varies from one node to another node, one city to another city. So that's what then we run the. Now in our example, we have taken only 5 metro cities: New Delhi, Bangalore, Mumbai, Chennai. Actually, okay. Four we are four we have taken. New Delhi, Bangalore, Mumbai, Chennai, Calcutta. Calcutta also taken. So now we get these are the nodes which are non-common. That means even though you may have 1,000, 10,000 vertices, but I'm interested to see the traffic which you get from source vertex 5 to source vertex 3 uh, using all our expertise actually. So once you do it, then you get the this data also. This is how the optimal paths. I only find optimal paths from New Delhi to Bangalore actually. You may see many multiple paths are there, but only this optimal path from New Delhi to Bangalore. That means it's minimize the cost, maximize the flow. So that's what we need to observe. Now this is another one, Bangalore to Pune. This one is New Delhi to Bangalore. This is Bangalore to Pune. This is Mumbai to Hyderabad. This is Chennai to Calcutta. This is New Delhi to Patna. This is the given by the real Railtel network. You have the dark red colors routers they are 10G, and you have the blue color is 2.5G. You have another color is 1G. Now this is how the complete picture of the Railtel network which is there. Now we construct a graph out of this. This is a graph, and how the red means they are connected with 25 to 100 Gbps. Remaining all connected with 25 Gbps. Maybe Delhi, Chennai, Hyderabad, Bangalore, Mumbai, all things may be connected with 200 Gbps. So different kind of network bandwidth is provided with the different kind of cities actually. Okay. Now this is how when we run the code, we get the output also like this actually. So this is very, very important to understand actually. Now, this is also another way of measuring the traffic matrix where the all 10 cities we can get the traffic matrix. And once we get the traffic matrix for 5 cities and 10 cities, then we can able to really understand visualization also. Similar thing here. I also show you. Hello. So now what we do, the last phase, we discuss about the, when we do real implementation, what are the issues we need to understand also. Let's see. Earlier we discussed that for a synthetic data, we consider the uh, 20 cities, we consider the 48 time intervals, and each interval is 30 minutes. But in the real-time data, every 5 minutes we take a snapshot. So by doing like this, we get the total data set about the time zone also. And this is how the cost capacity and demand, and given a cost capacity demand and given the 5 metro cities, then we construct the artificial matrix. Then we do the time zone. After doing this, we'll try to see. Now, this is how it really happens. You have the one side statistical methods which are there in the 1960s, 1980s. Now we are having very good linear programming algorithm, mixed integer linear programming algorithm for the solvers. Then we have the robustly we can build our math model with the five metro cities, 5 or 6. Then after that we run the telecom traffic matrix construction. We run the math model, get the telecom traffic matrix construction. Once you get the telecom traffic matrix, then you associate with the cost, capacity, as well as the demand. Then you run the optimization algorithm. Then after running optimization algorithm, then you go for the optimal routing path. This is how the flow goes. So what you really see is that how do we generate the graph model, and what are the graph we use for the direct graph, indirect graph, as well as the many other examples. What you really see is that we have the MPLS based BSNL network. The BSNL network is both are same. Its representation is different actually. This is how they look like actually. The right side you see 6 cities are there, and then left side also same thing. From that we can get the, what does that meaning actually? When I do the New Delhi to Mumbai or New Delhi to Thiruvananthapuram with sleeper, when you do this, particularly from Delhi to Mumbai, Delhi to Hyderabad, Delhi to Chennai, then we need to see one step below that how the data is getting into the Delhi routers. The data is coming through many network switches, many router switches. One is they're using New Delhi New Delhi, they may use other city to get the traffic data, and how many switches are there in every city, how many switches have been employed. All these things we can monitor using this kind of graphs actually. Here what you see, the actual physical topology in New Delhi like this. That means there are some routers, there are some switches where they communicate internally. There are some routers where they exchange with the outside actually. By doing like this, you can able to model the complete graph. That is called, you are constructing a logical topology of a undirect graph with the cost, capacity, and demand. And right side is basically they come out with the graph, but it doesn't give more clarity because it is a little bit not very well numbers. But the numbers, if you see, these all numbers indicates the edge number as well as the vertex number. Everything is given in this. Now you take the Mumbai city. So what you have seen here is that New Delhi side. Now you take the Mumbai city, how many routers are there, how many switches are there, and how they are configured, how are internally communicating, how are externally communicating. All these things are basically shown in the right graph here. Left side you see the graph actually. So that means you can construct the graph representation of telecom traffic data, and then model, then you convert into the traffic matrix, then you apply linear programming algorithm. So what you really see, the Mumbai city has got different kind of routers, different kind of switches, different way of configuration. Similarly, if you see the Delhi, they also different way actually. You can see Delhi here, they have differently actually. New Delhi. That means modeling, given a graph, solve using the linear programming solvers, finally solve the problem is one side. Other side also you have to see how many phone calls are conducted from morning 6 to 8. How do you keep track? Can we keep track different kind of data set actually? Okay. Now here you can see the result for the 14 cities. So what we have done, you consider the synthetic large graph data and generate the complete math model of the telecom pre-processing, and you compare with the actual pre-processing that happened 1 year ago, 1 day ago actually. So that means what? Once you have the complete telecom traffic data as a graph with vertices and edges, cost, capacity, and bandwidth everything if you have, then you can able to, when you solve this problem on the linear programming solver using the traffic matrix, then output, when you get output where the optimal routing ports are properly set and the program is running, now this is how the graphical output shows actually. This is how the output says what are the edge lengths. Here you can see many of the red curve vertices are cities and green is edges, and cities depends upon the time taken for the reading and writing, and we also take about the bandwidth and everything is given actually. So another example is that population learning. So what we have done in the, that means we focus more on telecom math model development. Math model, if you fine tune, you must get the actual real time traffic also same. Real time traffic means how many switches are there, how many routers are there, how the message travels, everything you need to record it. Once you record it, you should able to get idea about the overall number of phone calls, that is total amount of data, and about the cost, capacity and demand, everything is there. Then you solve the linear programming optimization solver. What we have done is small prototype, but if you really do complete all the districts in the entire city, you will be solving more than 10-20 billion kind of LP problem, and you have more than 100, 200, 300 shell script sheets, all things we need actually. Now we have the results for the, now this you can see results. What you really see in this result is basically actual, this is a typical telecom network, and we have taken the synthetic data, and then we have constructed more than 64 cities, this topology 66 cities. Now all these graphs, real time telecom network, banking network, many graphs, vertices are less, edges are more, number of parts also more. Because of number of parts are more, large amount of traffic can go from source node to destination node actually. What you really see is that the actual, one of the BSNL published data, you can say, where you have the different kind of traffic, different kind of routers, everything is there. Then you will be modeling as a graph. Once the graph is modeled, then you also have the vertex numbers, edge numbers, cost capacity. Once you have cost capacity as well as the demand, then you get the traffic matrix. This is how we can able to do. So what we really see is that different kind of routers, different kind of switches, everything is modeled actually. That means what we have done is we tried with the synthetic telecom traffic model. We also tried with some BSNL data. Then we have the four component validation of telecom math model. Number two is that how do you represent as a graph involving cost, capacity, demand. Number three is how to consider the traffic matrix. Now after traffic matrix, then how the all libraries are used to solve the network flow solver. Once you solve the network flow solver, you get optimal routing path from the given set of demands. Given set of demands means morning 8 o'clock to 12 o'clock, morning 4 o'clock to 8 o'clock is one kind of telecom traffic. Morning 8 to 10 is another kind of telecom traffic. Morning 11 to afternoon 2, traffic is more. So based on all the things, you should able to accommodate such a large data, large problem on the powerful supercomputer. And also, if you want to apply AI, you need the previous data. For the previous data, you can store every half an hour previous data. That means you need different way of storing the data at the pre-processing level, graph construction, traffic matrix construction level, as well as the arranging in the graph and AMPL solver output, the network control, all the things you require different kind of routines to support. Once you do everything, then you run the linear programming solver, then you get the optimal routing of the current set of demands. This current set of demands will change from time to time, because first we tried with morning 12 to morning 6, 6 to 8, 8 to 9, 9 to 10, 10 to 11, and 12 to 1, like that we have tried. All these things leading down to the optimal routing paths actually. And what you really see here is another example of right side. You can see all the cities of the 705 cities, and you have 3000 edges are there. Left side, you see the traffic, how it goes. Mumbai to Delhi, you have maybe 100 Gbps. 10 Hyderabad to Bangalore, 10 Gbps. Chennai to Calcutta, 10 Gbps. And Hyderabad to Mumbai also 10 Gbps. With this kind of high-speed connectivity, many cities which are there, they come under 1 GB bandwidth spectrum or 1 GB, maybe few nanosecond latency. Then we can able to run the complete application. Actually, when you run the complete application, optimal routing path identification is important. Visualizing is also very important. This we have to do actually. So what is important in the entire thing is whatever telecom network you give, data describing the network cost, capacity, everything. Second one is which problem to be optimized, that also we need to understand actually. These two are very important that we need to get idea. So I will take some, I'll conclude here. What you really see is the how the BSNL traffic data which we can visualize actually. So this is how we can visualize the data. So this is very idea of giving a how dense is the network traffic and how much is the data moving from one OD pair source to destination and what is the demand. All these things have been encompassing as well as the network topology. And now we can use to construct the traffic matrix, then process it through the linear programming that is called mixed integer linear programming. Then you get the optimal routing path again. So continuously you have to do for the days and months together. Every time interval you have a lot of pre-processing, lot of post-processing, so much work we have to do. Ultimately, aim is to smoothen the traffic so that your phone call should reach from origin to destination in shortest possible time. So what you really see is that these are the traffic metrics. Now, traffic metrics also has got many linear programming algorithm has got many variables we need to understand. Number of decision variables, constraints, equality constraints, inequality constraints, many simplex method, all the things actually. So now, what I'm covering lastly is that the telecom math model, what we are doing, telecom math model is basically the math model is very closely represent the Indian context where you take the population, you take the activities, you also take the affinity, you also take the map, all these things also you take it, then you model the complete telecom math. Once you model the telecom math, then you validate the model. To validate the model, you can use different kind of networks and everything. That also we'll try to see, and we'll close our today's presentation. Let me see results. Five minutes. Next person is come. This is completing. So before we conclude, so these are all the things which we need to get exposure for the large scale 5G telecom traffic, data processing, and how the supercomputing is connected, these things. What you really see is the abelian network is in the US. There are some cities in the West Zone, some cities in the east zone, they use the same logic, cost, capacity, and demand, and then they construct a graph. The set of graph is given, and right side you see the optimal routing paths from source to destination. How many edges it travels, everything they have given. Also, we also indicated the optimal routing path. Now we can see bottom below is the European research about the teletraffic application, and extreme right side is the German one. And Indian context, the CDAC MPP lab is one which we are doing. You have the logical topology, you have the real-time BSNL network, you have the rail-time network, you need to do your simulation. So ultimately, what is important for us is the telecom application, traffic engineering, networking behavior, congestion delays, bottlenecks, reliability. All things we achieve through the telecom traffic matrix construction, as well as the how to model the telecom traffic as a graph, and graph with set of set of vertices having a cost, set of edges having the capacity, and all things we take into consideration, and given vertex to the source vertex to the destination vertex, origin destination pair, what is the demand. So here, if you have 1000 OD pairs, 1000 into 999, that many is the total number of OD pairs. That means 1000 into 999, if you really count everything, how many variables you are solving, all the variables are going for the 10 million, 20 elements. But if you really take the entire Indian context and come out with the telecom math model and traffic and everything, you may be solving more than 5 million, 100 million, 200 million variables. That takes a lot of time on the computing. And now people are using GPUs also for things. So that means given a traffic, you can represent traffic as a graph with the cost, capacity, and then knowing the demand, then you construct the telecom traffic matrix. Telecom traffic matrix with the network topology and the complete data, use it and solve the linear programming and optimization problem. Then you get optimal routing paths. Optimal routing paths again you give to the from the head node, you can able to talk to the data extraction server and change the hardware software configuration also. So various components, traffic at the switch level, router level, metadata, that is one thing. Number two is that data extraction server, how do you get the data? Data extraction server pushing to the head node, how do you represent as a graph, cost, capacity, as well as the demand. After that, you solve the linear programming and mixed integer linear programming solver, mixed integer linear programming solver. Output gives the optimal routing path from origin to destination. That goes to data extraction server. Data extraction server again talks to the network and make the complete changes actually. So this is how the complete thing has been done. With this, I'm closing today's my talk. So I covered completely real-time optimization of entire telephone network using linear programming algorithm, where we solve some 100 million, 200 million variables, and where we need a supercomputing technology, and we use a lot of graph based algorithm, matrix algorithm, these things. With this, I am concluding. Thank you all. Some questions are there. I'll take some questions.
Thank you, sir. The participants can post their questions on the chat box. There's one question from Mr. Paresh Solanki. Can MPP LAB be available for research purposes?
Yes, MPP LAB is one of the objective is to make it available as an open source software so that one can solve many of the applications in finance domain, banking sector, and other areas, but it will take maybe 2-3 months to make it available.
Thank you, sir. Uh,
Thank you all.
yes, sir. Right now, I don't think there are any further questions. Um, so if there are any further questions, I think they can email their queries and sir might be able to answer them.